Good afternoon, everybody, and thanks for making it here. I know, there are lots of smart speakers out there. In fact, I'm missing some of the sessions that I wanted to attend as well. So thanks for being here. So view from the trenches, first principles. So I'm going to be talking about first principles. It's going to be a refresher of sorts. Let's get to it. Quick intro about me. I'm not really fan of doing these self-introductions. So when I say view from the trenches, you got to know, where I'm coming from. So the trenches that I've worked in are avionics, automotive electronics, data management, network security. Worked with a whole bunch of firms there. You can see that. I currently run a couple of software development studios. They do various things. My day job is, of course, managing software development at BAE Systems. I'm across pretty much anything to do with software there. So apart from that, I live in South Australia, and I love trekking there. Fun fact, the world's most beautiful city, voted by Architecture Digest, is in South Australia. So I'll leave you guys to Google that and find which city that is about. Cool. Few pointers. We'll reserve some time for Q&A at the end of the talk. I should be able to get through and have some time at the end. If in case we don't get through, I'm always available outside. And CppCon has a Discord channel specifically for this talk, so you can continue the conversation with me there. Source code snippets that I'm going to be showing are purely illustrative. They're not really production code, right? And they'll be available on my GitHub at the probably by the end of the week. Cool. Just to give some context, based on my experience with real-time applications, many of them are safety critical. So for instance, avionics, those of you who are from the avionics side will know DO-178B, right, has different software levels. So level A is catastrophic. So so for instance, engine, the software which controls the engine of the aircraft, right? If that fails, it's going to result in loss of life. So that's like level A. The flight management system, which the airplane pilots use inside the cockpit, that's level B. So that's the kind of criticality that we're talking about here, right? So reliability, maintainability, extensibility, testability, scalability. Now all these, right, are equal. Security, of course, and they're as important as performance, meeting hard real-time requirements. So software design is really paramount. You've got to get your software design, and software design, as you guys know, is not really a science, it's more of an art, right? So this talk actually will be focusing on first principles on all these elities, and there's a lot, but I really can't cover everything, but I'll try my best, right? So most projects I've worked on, they use older versions of C++, so C++ 14. So it's not that we can't move to C++ 20, 23, or 26. It's not a decision that we take lightly, right? So we're not looking for the latest and greatest features here. What we do is we deliberate a lot, right? Because these are things which concern, as I said, loss of life, defense of the country, things like that, right? So we can't use a feature just overnight. A lot of testing goes in, a lot of deliberation goes in, even before we actually move from C++ 14 to C++ 17, right? So, and if someone like, say, Bjarne Stroustrup says he's not really comfortable moving a certain feature into C++ 26, right? I guess you know which feature I'm talking about. That's got a huge impact, and we're going to be deliberating on that, right? So we tend to take the tried and tested path, and that's with good reason. So before I jump in, I'd like to acknowledge the works of all these great gentlemen here. My approach has been influenced to a large extent by what they do. Cool. So I'll be covering design patterns. Not everything, there's a whole lot of them, but as many as is possible. Memory and resource management performance, some performance tips, how you handle globals, and some general tips. All right, let's start with design patterns. So we all know that adding types, right, with C++ classes is going to be easy. So this is just a pedagogical example here. So you got class shape, right? And you got class square, you got class circle. It's pretty easy to keep adding types. But what about adding operations? Now, when you try to add a new operation, you got to modify your base class. You got to modify, the complete inheritance hierarchy, right? You got to modify your child classes as well. So, how exactly can you, go about doing this in an elegant and what can I say, seamless way, right? So that's where the visitor pattern comes in. So what you do here is it's a behavioral design pattern, and clearly it's a separation of concerns, right? So in the previous snippet of code, you have all these operations, rotate, pivot, and transform. If you look at the visitor implementation, you separate the operations into a hierarchy of its own, right? So you got visitor, shape visitor, you got rotate as a separate class. So similarly, you can have pivot as a separate class. So you clearly separate the abstraction of what the shape is from what it's actually going to be doing, right? So that's achieved using the visitor implementation, right? You separate the operations into a separate hierarchy. Now, within the shape abstractions, you can see that I've got an accept function there. It can be any name. It's not really a must that you should have it as that name, right? So you basically call the visit function from within your abstraction, right? And you can see that there's double dispatch happening here, right? So at runtime, you can decide what kind of operation you're going to happen, what kind of operation is going to happen, and you can also decide at runtime, what shape you're going to be asking that operation to be carried out on, right? So this basically separates the concerns, right? So you can actually completely go on a different track without being influenced by your shape abstraction, right? So this is the classical way in which you implement, the visitor pattern. And, you can see there's a lot of runtime polymorphism, virtual functions coming in here. So the modern take, C++ 17 offers, the variant. It offers the std visit. The bottom right, the main function, as you can see, I've got a std visit, right? So this basically makes it really easy to implement the visitor pattern. So you can see there are several advantages here, right? So rotate and pivot. Previously, I had to have like a hierarchy there, but rotate and pivot here can be separate classes of their own. There's no need to actually have, base class. You're not restricted by any base classes here. So once again, all that's taken care of. The double dispatch is handled by the std visit there. And you can very easily add types. So you've got to change your variant there. You can easily add operations. You just keep adding classes. And it's pretty easy to just call the visit function, right? So this is a great feature. In terms of, performance, this is definitely much more performant than the classical implementation, right? Because you're not having virtual functions, you're not having any indirection calls here. And it's loosely coupled, it's elegant, it's performant compared to the classical visitor solution. Now, there is obviously a downside, and there has to be a certain level of recompilation which has to happen here. Right, let's move on to the next one. So when you think of adding new operations, think of the visitor pattern. All right, let's look at this bit of code here. What do you think is wrong here? Just have a go.
Pure virtual implementation.
Sorry?
It looks like a pure virtual function with an implementation.
Yep. So that's definitely one red flag there. And as you can see, the hierarchy is pretty unwieldy, right? There's a lot of inheritance happening here. And like a friend here pointed out, calculate takeoff weight in the base class, the aircraft. And by the way, this is from my avionics days. So takeoff weight is just one of the functions that we actually encapsulate within the aircraft. So calculate takeoff weight is supposed to be a pure virtual function, but there's a concrete implementation as well. So that kind of gives the indication that the author of this class didn't really intend for it to be a base class, right? And as you can see, there's regional jet, class regional jet on the left panel. That's also making a call to the aircraft calculate takeoff weight. That's where am I pointing? Okay. There's class regional jet on the left panel. There's public, it's inheriting from public aircraft, and it's also calling the base class implementation, right? So these are fundamental flaws. You don't really use inheritance to reuse code. That's not the way you use inheritance, right? This is a very wrong way in which you use inheritance. And I mean, this is what probably a lot of us may have done over the years. And the other thing is, of course, there's a very nested deep hierarchy here, where it can lead to a very complex hierarchy, right? So the key thing here is calculation of takeoff weight, right? So calculation of takeoff weight is something that's got to be accomplished here. That's what can you say? That's basically what each of these classes is trying to do. And regional jets like, there are various regional jets out there, they have a different way of calculating takeoff weight. Whereas the big airliners like Airbus and Boeing, they have a different way of calculating takeoff weight. So that's what's represented here. Now, if you're trying to calculate takeoff weight, say for a regional jet, you've got to have a strategy in place, right? The strategy of how you calculate takeoff weight for a regional jet is going to be different from the strategy that you use to calculate takeoff weight for a large airliner. So you strategize, and that's what's the strategy pattern is all about. You pull out the strategy as to how to calculate takeoff weight into a separate hierarchy of its own. So as you can see, this is all mixed up. It's all mixed and matched. Now, you pull that takeoff weight separately into a hierarchy of its own. So you've got the takeoff weight regional strategy class, you've got a takeoff weight long haul strategy class, right? So that's what you do. And that's exactly what the strategy pattern is all about. So it allows the addition of a new implementation of algorithms, right? So for takeoff weight calculation, you have a separate set of algorithms. And it also allows you to select that algorithm, right, at runtime without actually modifying the client's code. How do we do that? So all that you do is actually you have a pointer that gets injected, right? So regional jet, it just basically uses a strategy that it wants to use, right? So it's not really going to be bothered about, how a long-haul jet calculates weight. It's all that it's bothered about is its own strategy. So that's what is that's what you see here. So you got class regional jet actually taking a pointer to the regional weight strategy class. So going back to my initial point, saying that inheritance is not really inheritance can be misused, and it was misused in that previous snippet of code. So you got to prefer composition to inheritance. So don't needlessly inherit. When there is an absolute necessity to inherit, that's when you inherit. You do not really just use it willy-nilly, right? And all that you need to do here is just simply embed the pointer to the strategy. And then you just call the weight calculator, which is implemented in the strategy class. So that gives you control over the strength of the coupling, right? So you're able to enact a certain level of looser coupling here, right? And obviously shorter compile times. So once again, clear separation of concerns here. There's, implementation details can be abstracted out, right? So multiple operations will need, obviously, multiple strategy-based classes. So that's a bit of a downside, but it's manageable. Now, let's look at, the modern take. The modern take says, and there's no ready-made pattern, like, the visitor implementation, there's no ready-made pattern here. But of course, you can use concepts, you can use ranges, STD function, right? So you can use STD function to store calls to lambdas, function pointers, and the like. So that's basically how you come out with the strategy pattern. It's still relevant. So whenever you think of maybe how you want to implement something, a specific functionality, you want to come out with a strategy, right? So that's when you use the strategy pattern. Okay, let's move on. This is an example from my days with the medical imaging side of things. Those are CT images, computerized tomography images. And so we have multiple views, right? So I think this is the spinal cord, I can't remember. So you've got different views. You've got the anterior view, the posterior view, lateral view, cross-sectional view, whatnot. So you've got all these views and you've got to display it on a screen, on one screen. So what's the naive way of doing it? You create threads, right? So posterior display, you create a thread. Lateral display, you create a thread. Anterior display, you create another thread. Once again, question. What do you think is wrong here? Okay, so it's kind of related to what I was talking about previously. So as you can see, you got your thread management logic mixed with your display logic, right? Once again, that's breaking the single responsibility principle. You guys have heard of solid, right? So you've got the single responsibility principle. Now, that's broken here. So you've got all your display logic mixed with your thread management logic as well. That's not good, right? This is what we should be doing. Your thread basically doesn't need to know what it needs to do, right? You just give it a task. You just command it to do something, and it's supposed to do that. Right? It's just a worker thread. Why does a worker thread need to know details about what it's supposed to do? That's the key idea that needs to come out here. All right? So as you can see, there's a unique pointer to a command. So you just command your thread to do something. And that's pretty much the command pattern. So you need to separate your thread management logic from the actual command that the thread is actually trying to carry out, right? So that's nothing but the command pattern. So your guiding principle here is once again the single responsibility principle. You issue a command to the worker thread and you ask it to do, maybe paint a display, whatever. So it really is a dumb thread. It doesn't really need to have intelligence. So there's a decoupling there, once again. And that's where you use the command pattern. So as you can see, that's the hierarchy that I've kind of come up with. So you've got like a command abstract interface. You got the posterior display command, anterior display command. You got its own hierarchy. So it's got its own hierarchy, right? And then from your main function, all that you need to do is you just schedule the thread. You inject which command you want the thread to execute. So once again, pros, as I said, you're separating what needs to be done. Cons, yes, obviously runtime performance. Overhead due to the additional indirection here, allocation of polymorphic objects. This can result in fragmentation of memory. All those are there. Now, the astute ones among you will notice that there's a very subtle difference between the strategy pattern and the command pattern, right? So this is something that's got to be a talk of its own, but pretty much all design patterns, they're structurally the same. It's the intent which actually differs, right? So now if you have an object and you really don't need to configure the other abstraction with this object, right? So in this case, the example that I gave is the thread really doesn't need information about what operation it's going to be, working on. In order to, exist as a thread. It doesn't need to know what operation it's going to be running, right? So that's when you talk about something like the command pattern. So you just basically issue a command. So to give a very simple example, think of a calculator, right? The calculator has like add, subtract, multiply. You can add hundreds of commands, right? Maybe you want to say, play Candy Crush. Add that as another command to your calculator. Now the calculator still exists whether you have those commands or not. So all that it needs to know is what command it needs to implement. So you add a button there. And that's basically how this command pattern works, right? So you don't really mix both these abstractions. All right. Once again, the modern take, there's no ready-made solution like std visit with the visitor pattern. There's no ready-made implementation here. But once again, as you guys can see, you can use smart pointers. You can use std function to kind of, move away from older versions of C++ and make the implementation a lot more elegant. Right. So key takeaway, whatever needs to be done to execute a piece of work, that's when you think of the command pattern. This is pretty much, I think, something that all of us would have encountered. I didn't include this for the sake of completeness. So integrating incompatible interfaces. So as you can see here, DICOM images. So this is an example from my medical imaging days. And those of you from the medical side will know that CT, ultrasound images, these are stored in DICOM format, right? So we had a third-party image provider. And they stored the images in a different format. Now, both these had to interact with each other, right? Incompatible interfaces. So as you can see, DICOM image has store image, retrieve image. The third-party image has something similar, but a different interface. Now, how do you actually get these two to talk to each other? Very simple. All that you need to do is that's where the adapter pattern comes in. We basically wrote a wrapper, which calls the third-party implementation, right? So as you can see, that proprietary image adapter, the store image function, so that's overridden from the DICOM image class, right? That basically calls the third-party image function, the tp_image.write-to-disk function that you see. That's what, actually, let me use a laser pointer here. Yeah, so the TP image, write-to-disk, that's the third-party implementation, right? So it's basically written just a wrapper over it. And this is nothing but the adapter pattern. So think of, two pipes in real life. So you got one pipe with, maybe a 1 millimeter bow and another pipe with, 0.5 mm bow. You got to connect these two pipes, right? And that's all what the adapter pattern is about. So you just try to connect to incompatible interfaces. So it's a structural design pattern. So structural patterns actually talk about how classes can, objects compose together to form something different, form a different entity. All right, let me get this out of the way. So different types, different ways of actually writing an adapter pattern. You've got the object adapter, where you actually encapsulate the object in your implementation. Or you got the class adapter pattern, where you actually try to inherit from the class that you're trying to adapt, right? So that's not very popular, and that's not recommended as well. The object adapter pattern composition is what is preferred. So pros of this, you easily can integrate third-party implementations, right? You get a lot of flexibility in like mixing and matching stuff. Cons, of course, as always, runtime performance considerations. You can overcome this to a certain extent by using static polymorphism, right? Templates, function adapters, and stuff. Once again, there's no ready-made implementation in modern C++ where you can say std adapter. There's nothing like that. So, but C++ 20, it offers range adapters, right? So, you guys have worked with range adapters. How many of you have worked with range adapters, right? So, there's a transformation which happens, right? So, you can actually use std views, transform. You can adapt a certain a range of elements by applying a function. So that's basically that's how they use the adapter pattern. So yeah, once again, this pattern is It's pretty popular. It's still relevant. So it's good to know how to use it. All right, let's move on. So this is when I was with the network security side of things. So this is a pretty bad representation of endpoint management. So by endpoints, I refer to like it could be laptops, it could be your handheld devices, it could be your servers, anything. So endpoint management talks about actually managing all these devices, right? So we get to monitor these devices. So we got to receive events from these devices, and then we need to take a call, right? So we basically try and observe all these devices. And endpoint managers sit at different levels of the hierarchy. So you could have endpoint managers sitting maybe at a data center. You could have endpoint managers sitting at maybe at the LAN level. So they do two things. They monitor, as well as you can push down policies from an endpoint manager. You can push down policies to, say, maybe your laptops. I mean, like that's pretty much what happens in all our organizations today, right? So we have policies pushed down from a certain team, restricting us from probably visiting certain websites or stuff like that. So that's endpoint management. So I think it should be pretty obvious what pattern I'm talking about. I'm talking about the observer pattern, right? And there are two types of observer patterns here. So you got the push observer and you got the pull observer. What's the push observer? So you got the observed endpoints, right? And you got the manager sitting on top. Now, if a whole bunch of events goes up to the manager, and the manager basically hasn't really explicitly asked for something, it's just getting a whole dump of events. It's just getting anything that's being pushed to it. That's the push observer pattern. The pull observer is when, as a manager, you ask a specific endpoint for something specific. You ask for some specific state. That's when you're pulling specific information. That's the pull observer, right? So we, used a hybrid a hybrid approach where we use push observers at a certain level and pull observers at a certain level, depending on our use case. So once again, this is a behavioral pattern, as you can see here now, the push observer, there's no coupling, because pretty much any event gets pushed up. And same way the observer, the manager, doesn't really get to, it doesn't really control what the observed person is sending across, right? So there's no coupling there. On the other hand, for a pull observer, as you can see, look at the second function there. So you got like virtual void update. So this is what I'm talking about. This is this is a very simple, simplified version of it. You specify which endpoint you're actually trying to observe, and you also specify the property that you're trying to observe. So that's the pull observer. So there's definitely a certain degree of coupling here. It becomes tightly coupled. Now with the push observer, the problem is that you have to filter the events. You're getting a whole bunch of events. You might get, millions of events flooding across, right? So you got to write a filter to filter the specific events that you want to look at. Modern take, once again, there's no ready-made solution to implement this observer pattern. But you can use modern features, STD functions, shared and weak pointers to manage, you can use coroutines as well. Coroutines are also, to a certain extent, you can manage asynchronous events and callbacks, right? So using coroutines. So usually the observed object, the endpoint, that holds a shared pointer to its state. And the manager holds a weak pointer to the object that's being observed. So you can dereference that weak pointer to know whether that shared object, that observed object is still in existence. So you use a weak pointer to understand that. So that's basically, I would say modern C++ just gives you the tools. You'll have to know how to implement this pattern. Cool, so let's move on. Optimizations, yep. You can implement it as a class template, but then you need a certain concrete implementation as well. let me go back to this example from avionics. So V-speed calculators. As you can see, there are two classes here, so FA and JA. What do you think, what are the problems here? So like, let me give you some background. The FA actually handles avionics, aerospace in the US, and the JA no longer exists right now. I think it's been, superseded by some other organization in Europe. But at that point in time, there was the JA and the FA way of doing things. So V-speeds are what actually, an aircraft is supposed to attain. So, there's a certain speed at which an aircraft can take off. There's a certain speed at which it can land. So the FA had a certain way of calculating this. The JA had a different way of calculating it. Now it's all harmonized, right? So there was a time when there was a disparity. So looking at these two classes, what are the problems that you can see? It's easy to misuse. Okay.
As in, if I don't know what type I'm dealing with, because it's maybe been dynamically allocated.
Yep. That is one of the problems. The other thing is, you can see that, the FA, Airstream FA class, anyone opening that header file is going to see the physical dependency on the FA V-speed calculator, right? Similarly, the JA class. So it's all private, but then it's private just only to the compiler. Private only at that level, at the binary level. But if someone opens this header file, they're going to see that physical dependency. And they're going to get to know that, okay, this class uses the FA V-speed calculator. This class uses the JA V-speed calculator. Now, the other thing is, so we have an abstraction which is for an aircraft, which is also encapsulating the V-speed calculation, right? So that's once again bad. So there are two problems here. Once again, it's breaking the single responsibility principle. Data hiding is lost because, to a certain extent, not data hiding, not really an ideal way. As I said, there's a physical dependency. That's the key thing here. There's a physical dependency on those two specific implementations, which is not really good. And just imagine, multiple types of aircrafts. These are just only two aircrafts that I've shown here. So Airstream is a type of aircraft. I've kind of played around with the words here. Those of you who are from that side will know what I'm talking about. So there are multiple aircrafts, and each of these aircrafts have unique V-speed calculations. So just imagine the flurry of classes that you're going to have, right, with multiple types of aircrafts. So there's going to be, and like our friend pointed out here, there's going to be duplication of code. One side effect is that it's using the same name, which is not really good. From a maintainability point of view, if you're going to have duplicate code, just imagine what problems you could have. So, and like I said, the physical dependency on the V-speed calculator. All right. Now, how do we get over this problem? Once again, pull the abstraction out, right? So V-speed calculator, the aircraft knows that it needs a V-speed. So this is not a case like, not like the thread example which I gave you. The thread didn't really need to know what operation it's carrying out, but this is different. The aircraft needs to know what V-speed calculation it's actually, it knows that it needs a V-speed calculation to exist as an aircraft, right? No aircraft can exist if it doesn't really have a V-speed to take off or V-speed to land. So it does know that it needs something like that, along those lines. The key thing is that you've got to separate it into a different hierarchy. And that's what's done here. So as you can see here, if you look at the airstream.h file, it's just now taking a unique pointer just to the base implementation of V-speed calculator. So anyone opening that header file is not going to know whether I'm going to be using an FA way of calculating V-speed or a J version of calculating V-speed or maybe an Alaskan way of calculating V-speed, whatever. All it knows is, hey, I've got this V-speed calculation to be done. Now you go into your actual implementation. That's airstream.cpp, the lower right half. That's where you modify your implementation, right? So you can actually point to a specific V-speed calculator. You instantiate a specific V-speed calculator that you want. So clearly a separation of concerns here. And this is nothing but the bridge pattern. You're creating a bridge between the aircraft and the V-speed calculator, two kind of independent entities. You can't really say independent, codependent entities. You're creating a bridge between both these entities. So a very simple way of looking at it is you separate the abstraction from the implementation, right? And the most simple and elementary form of the bridge pattern is the Pimpl pattern, the Pimpl idiom. We'll come to that later. Now, so like I said, you separate the V-speed calculation, you put it into a different hierarchy. You can easily change implementation details, right? So because you're not bothered about the header file, you're not going to be modifying the header file. Now, no one can actually see what type of V-speed calculator you're using as well. So there's no physical dependency, or remove that physical dependency. So there are similarities, once again, between the bridge and the strategy design pattern. I'll go into that. I won't waste your time now on that. If you have any questions around that, I'll be happy to answer later. So once again, there's a downside. Performance can be affected. So how do you improve performance here? So what you can do is there's the concrete implementation, whatever is frequently used, right? That can come out, and what is not that frequently used can actually hide behind the pointer to the implementation, right? So that's called the partial Pimpl idiom. That's one way in which you can actually try and improve your performance. Once again, the modern C++ doesn't offer any ready-made solutions. Of course, you can use modules, right? Modules actually provide that compilation firewall. Smart pointers, that can also be used. So that's pretty much it. That's the bridge pattern. So when you think of decoupling from an implementation, you think of the bridge pattern. All right, let's look at a few additional patterns, right? So our virtual function performance overhead. This is something that our friends in the low latency side of things, game developers, will always crib about. So how do you actually overcome that? I guess many of you already heard of the CRTP pattern. Now, CRTP actually replaces the runtime relationship between a base class and its derivatives, using virtual functions. You don't use virtual functions with a compile time relationship. So that's CRTP. It's pretty involved how you actually implement it. I won't go into the details of how we do it, but there are some cons as well to CRTP, right? There's no common base class. Everything that comes in touch with CRTP becomes a template. And unless and until you're actually dealing with static types, it really doesn't make sense to use CRTP everywhere, okay? So C++ 20 concepts could potentially replace CRTP. I haven't played around with it too much, but yes, you can use a concept to define requirements, right? You can restrict the functions. You can say, you define requirements for a set of types, and you can actually restrict the functions that, only those types can actually, which meet those requirements, will come into play, right? Now, the next thing is, do you really need inheritance? This is something that, not many of us think about when we design classes. Inheritance is a very powerful concept, and we just need to put in a lot more thought before we try to use inheritance, right? So you just can't inherit for the sake of inheriting code or reusing code. And there's a really nice talk. It is old, it's from 2013, but it's still very relevant. So Sean Parent, how many of you have already watched this talk? Okay, cool. And that's a nice quote, and that's from Sean. Inheritance is the base class of evil. So think of this before you inherit again. And actually, the type erasure pattern came out of his talk, right? So that's a nice idea to bear in mind. And you got to remember that the tightest coupling relationship is friendship. Inheritance comes second. So you got to really think twice before actually using inheritance. So that's that. All right, so what have we covered so far? We've covered the visitor, strategy, command pattern, the adapter pattern, observer, bridge, concepts, type ratio. Yeah, so, all right, there's some general class tips now. Okay, once again, I go back to my, you guys are going to get sick of this, but there's a calculate takeoff weight public interface here, right? And there's also an implementation happening here. Once again, my question, what do you think is wrong here? Okay, so two things. One thing is it's providing a public interface, and it's also trying to do the implementation. This is something that, as I keep saying, you've got to separate concerns here. When you're providing a public interface, you've got to be really careful because your clients are going to be using this code. Now, if you bring in your implementation details as well, it's going to be really difficult at a later point in time to change the implementation, to change the interface, right? So you don't really do this. So if you're providing a public interface, it should just do only that. Shouldn't be also doing bits of the implementation. And that's what is done here. So while it's two principles, more than one responsibility, and you're also not really hiding your implementation, right? It might seem pretty contrived, but there are cases where I've seen this happen, all right? So all that you need to do is you just provide a pass-through from your public interface to maybe a private implementation. That private implementation can be virtual, all right? So that's what I'm talking about. So all that you need to do is provide like a very dumb public interface, right? Depending on your use case. Just provide only what your client needs. Do not provide anything more than what's required. And that's what's done there. So as you can see, that's the public interface, the get takeoff weight retaining a double, right? It's not virtual. It's just dumb public interface. That's it. Now you can hide your implementation. All that it needs to do is it just needs to call the virtual implementation, which is protected, right? So that way you're decoupling your implementation from your public interface, right? So both things can evolve separately at different rates. So you make public functions non-virtual, virtual functions non-public, and you provide a public interface and a private protected customization interface so that both can progress independently without actually breaking user code. So that's the key thing here. So once you actually have a contract with your user, it's difficult to break the contract, right? So it's easy to start with something like this. And then you change your implementation, and that change is actually transparent to your customer, right? So this is nothing but the non-virtual interface idiom. So when you provide an interface, always ensure that it is, not always, it's good to actually provide a non-virtual interface. Depends on your use case. Good to know. The next one is the Pimpl idiom. This is what I was talking about. The simplest form, the bridge pattern, is the Pimpl idiom. This is nothing but separating your abstraction from your implementation. So if you can see this bit of code, it does have knowledge about the protocol analyzer module. It does have knowledge about the implementation, the packet inspector implementation. All it does is, that's a forward declaration. So the implementation is actually not in this file. So it's out separately in a different translation unit. And you just have a pointer to the implementation. So once again, your implementation can proceed at a different rate on a different track. So why is this useful? Shorter build times, right? Obviously, your build times are going to get really short. You're decoupling the implementation. The other thing is, by actually hiding the implementation, you're preventing, what can you say? Names from being, a mix-up of names, right? So there's no name hiding going to happen. So you're not actually going to pollute the space by having multiple names, probably names which are like colliding, names which are identical. So name hiding is avoided. Cool. This is a very straightforward pattern. Now, non-member, non-friend functions. Once again, another question to you. I think it should be obvious by now. Why do you prefer non-member, non-friend functions?
They have the lowest coupling.
Sorry?
Lowest coupling.
Yeah, awesome. So better encapsulation, right? So there's no dependency on your private protected implementation. So there's no coupling with that. So, and if you do not know what those private protected stuff is going to be, you're going to force yourself, it forces you to write generic code. You're going to write code which is not dependent on the implementation. So that's, these are things that sometimes I didn't know in the initial days in C++. You always start off by writing, say, a member function. You don't really think, hey, why do I need a member function? Do I really need a member function? No. First, this should be on the top most of our minds. So you prefer non-member and non-friend functions. So that basically ensures that there's better encapsulation. You don't really get to peek into the details of the implementation, right? So you also break monolithic classes. Your classes are not going to be bloated, right? So that's another key thing to bear in mind. This is actually implementation that's out there somewhere. It's a single function, and it's a really bad example of how not to implement. A bad example of how to write a function, right? So you can see a lot of duplication of code there. You can see the if-else ladder. There's a lot of laddering happening there. So don't write a function like this. So one function, one responsibility. Be very cohesive when you write a function. All right. This is my favorite slide. As I keep on saying, follow the single responsibility principle. You build high-level abstractions from low-level abstractions. Good example of how not to design a class. So can anyone identify what this is? All of us have used it. Which library am I talking about? Yep. So this is a very good example of how not to design a class. And with due respect to the designers of the string library, they designed it at a time, I think their considerations are different. The string library was not supposed to be included in the STL. But this is really a horrible way to design a class. So you've got 100+ member functions, right? It duplicates many of the standard algorithms, right? So you guys know we have the string version of find, and you have the standard way of doing a find. Doesn't stick to indexing. You can actually index into a string. You can use iterators. So, it provides both. So those are not really good ways to do it. So minimal class is what you should be actually targeting. It's easier to comprehend, easier to maintain, easier to deploy, right? So you don't really do too many things. If a class tries to do too many things, you're actually headed down the wrong track. So monolithic classes, they try to do classes like this, like the string class. They try to do too much, and they don't do it well. So, and also obviously risks breaking encapsulation. If you've got 100+ member functions, what exactly are you hiding in your class's implementation, right? That's really an open question. Okay, what am I talking about here? What's that emoji about? Any guesses? It's a very sad emoji, right? So it's downcast. So I'm talking about downcasting here. And as that the part that I've highlighted in red, there's actually that's the part which is in question. So you got this pointer to the base implementation, but then you're dynamic casting to the concrete implementation. So this clearly shows that your base class abstraction is incomplete, right? And I've seen this happen several times. So as you can see, you got the CT master view class, which just only has an L section and a C section display function. Okay, only these two functions. And then this derived class, adds its own implementation. It adds some more functionality. And if you go further down, this adds some more functionality. Now, this clearly shows that this base abstraction is not really sufficient. It doesn't really, meet the needs. So this is bad. And you should actually be relying more on compile time checks. And that shows a better design, right? So you shouldn't be relying like this on runtime casting, right? So that shows that your design is not really going to, I would say, it's going to be brittle. So this is a very brittle design. It can break at any time. So you should be using C++'s type system. It shows that you're actually working in tandem with the compiler. You have like a consistent view of what's actually intended, right? So this is once again a very bad way to design a class. Right, let's move on. Performance tips, yep. This is what everyone knows. Don't really use order of n square algorithms. Don't use anything that's going to be exponential. Good examples are like logarithmic complexity, set and map operations. Linear complexity, you have for each vector insert. And this is, I think, pretty straightforward. I don't have to explain anymore. Okay, let's look at this snippet of code. What could be improved here? So take a look at the if part, right? So we've got if my string equal to hello. Right, so this is an implicit conversion, right? So that literal has to be converted into a std string. So the key thing to do is to actually provide as many overloads as you can, so that you're actually helping this to move along faster, as you're avoiding that implicit conversion. And implicit conversions create temporaries, right? Which is not really good. So you provide the required overloads. Anytime you're working the sequence, you got to prefer vectors. Why? Because of all this, right? Vectors, when you're talking about sequences, I'm not talking about the other, I mean, like if you need a map, then yeah, go for a map. But when you're talking about sequences, always prefer vectors for these reasons. Space overhead is very low, fastest access speed, and they're almost certain to have the fastest iterators, right? So that's another thing. Let's look at this as well. Insert in a loop or insert in a range insert. What do you do? Which would be better? So if you look at the first one, if you actually try and insert in a loop, that's going to, it's order of n. Each insert is order of n. But when you do it in a loop, it's going to become order of n squared, right? So always prefer the range insert. That basically actually tells the compiler what you intend, and that's going to make it easier to optimize, right? So that's more performant. All right, so let's move to this one. Resource acquisition is initialization. This is pretty much a very standard algorithm that's used. We have a resource, right? We have a resource, and then we control the lifetime of the resource. We actually initialize it in the constructor, and we destruct it, or destroy or close the resource in the destructor. That's what the raw idiom is all about. So how does actually the language help us? Use unique pointers, use shared pointers. If you're working with multi-threading, use lock guards. C++20 offers the JThread. Let's look at this now, compiler behavior. How exactly is the compiler going to behave here, right? So you got shared pointer, you have OpenDP connection, and it actually tries to initialize two ports. Now what could go wrong here is there's no defined, this is not really, it's not really set in stone. So basically interleaving can happen here. So memory can be allocated first. So like the new can fire for both the ports, right? And then after that, the constructors can start getting executed. Now, if one of the constructors fail, you already got memory allocated for both the ports. And that could result in a memory leak if one of the constructors fail. So always do this. Have explicit resource allocation in your own statement. And that kind of, gives the resource, and give the resource immediately to the owning object. So that prevents any memory leaks from happening. Well, for the sake of completeness, always use smart pointers. And if folks are working with C code, don't mix malloc with delete, new with free, standard things. All right, let's talk about globals. So you got here in different translation units, I've defined OS, I've defined a global logger, and then right at the bottom there, I call os.initialize. So there's something called the static initialization order fiasco. Now, we don't really, it's not defined in what order it's going to be, defined, so to say. So if, let's say, OS is not initialized, OS is not created, this could result in a crash, right? So one way to actually get over this is to use something called the first use idiom. So instead of actually depending on, when it's going to be initialized or defined, you explicitly call OS, initialize it, and then after that should ensure that it doesn't break. Or otherwise with C++20, use C++20 modules, because header files just go out the window, right? If you use C++ modules. So that's another way to actually get over the static initialization order fiasco. All right, so if you must have globals and static objects, initialize them carefully. And obviously static objects, global objects increase coupling. If you're multi-threading, you got to use the primitives to avoid data races and stuff, right? So if you can avoid And if you come from the distributed systems world, obviously everything is using pub sub or message queues. All right, some general tips. This code actually crashed. It worked a few times and it crashed sometimes. So let's look at the if loop there. What actually was the problem here is that it's not really a logical AND there, which we are talking about, that the logical AND operator was overloaded. So then this becomes a function call. And C++ doesn't define the order of evaluation of the arguments. So what happened in this case was pam.start, right? That got called first, and PAM was not initialized. This is what I'm talking about here. So the logical AND was overloaded. PAM.start got evaluated first. PAM was not initialized. It crashed. And actually, this resulted in network filtering not happening. Now, this doesn't happen 100% of the times. 8 or 9 out of 10 times, it might work. But different RHEL versions, different OS versions, different GCC versions, argument-dependent lookup. All these can influence actually how this gets evaluated. So don't depend on the order of evaluation if you're overloading it. So don't overload the logical AND and logical operations. All right, let's keep going. Yeah, this is almost similar to that. You really can't say, which count is going to be 6, right? So don't do something like this. It's pretty straightforward, maybe silly, but then yes, it does happen in production code. So it's still not there. I mean, function argument evaluation order is still unspecified even in the latest versions of C++. Of course, C++ 17, argument sub expression always happens left to right, but still don't depend on the order of evaluation. Do something like this. Make it explicit. Right. Once again, what can go wrong here? How would this code have behaved? Look at the mem copy there. That's, once again, not a very good thing to do, right? So you have constructors which actually construct objects in a certain way, destructors which destruct objects in a certain way. Constructors have knowledge about virtual functions, your vtables, your vpointers. Mem copy is pretty dumb. It doesn't know anything about it. So if you're going to mix mem copy with code, right, you've got to be watching out for undefined behavior. So just avoid using mem copy on non-plain old data types, all right? So that's another thing that I learned over the years. Always compile at the highest warning level, right? In my line of work, we just don't ignore any warnings. If you have warnings from a third party, always use hash pragmas, disable the warnings if you know what's happening. I'm not really recommending that you disable warnings. Know what you're disabling before you actually go ahead and disable the warning. Cool, I think that's pretty much it. My 2 favorite authors, they say keep it simple, right? So remember that. My take on it is do one thing at a time, do it well, all right? Final words, I like this quote from Gordon Bell. The cheapest, fastest, and most reliable components of a computer system are those that aren't there. Obviously, we'll be all out of work if we follow this, but then the essence is that, you got to write only if it's needed, write software only if it's needed, do only what's needed. Don't write anything unnecessary. Right? So aim for clarity, testability, avoid pre-match optimization, single responsibility principle. I've been talking about this right through my talk. That should be your guiding light. Minimize duplication. So get your design right? You got all these latest and greatest features there, C++ 23, 26, but new features are not going to get, not going to fix your software. Doesn't really fix if you got bad design. All right, so get your design right first. Cool, that was all I had. Thank you for your time.